All right. Okay. So, I think I just did. I just I did. Okay. I just wanted to make sure. So, debating. Kind of want to just go through another chapter of that. Section. All right, let's do it. Chapter 11, Chemistry, Openstax, Solutions and Colloids. 11.1, the dissolution process. 11.2, electrolytes. 11.3, solubility. 11.4, colligative properties. 11.5, colloids. Introduction. Coral reefs are home to about 25% of all marine species. They are being threatened by climate change, oceanic acidification, and water pollution, all of which change the composition of the solution known as seawater. Dissolved oxygen in seawater is critical for sea creatures, but as the oceans warm, oxygen becomes less soluble. As the concentration of carbon dioxide in the atmosphere increases, the concentration of carbon dioxide in the oceans increases, contributing to oceanic acidification. Coral reefs are particularly sensitive to the acidification of the ocean, since the exoskeletons of the coral polyps are soluble in acidic solutions. Humans contribute to the changing of seawater's composition by allowing agricultural runoff and other forms of pollution to affect our oceans. Solutions are crucial to the processes that sustain life and to many other processes involving chemical reactions. This chapter considers the nature of solutions and examines factors that determine whether a solution will form and what properties it may have. The properties of colloids mixtures containing dispersed particles larger than the molecules and ions of typical solutions are also discussed. 11.1, the dissolution process. By the end of this section, you will be able to describe the basic properties of solutions and how they form, predict whether a given mixture will yield a solution based on molecular properties of its components, explain why some solutions either produce or absorb heat when they form. An earlier chapter of this text introduced solutions, defined as homogeneous mixtures of two or more substances. Often, one component of a solution is present and is at a significantly greater concentration, in which case it is called a solvent. The other components of the solution present in relatively lesser concentration are called solutes. Sugar is a covalent solid composed of sucrose molecules, C12H22O11. When this compound dissolves in water, its molecules become uniformly distributed among the molecules of water. Here's an equation. The subscript AQ in the equation signifies that the sucrose molecules are solutes and therefore individually dispersed throughout the aqueous solution. Probably better pronunciation is because it's derived from aqueous. So I've heard it that way before, but I always say aqueous. Although sucrose molecules are heavier than water molecules, they remain dispersed throughout the solution. Gravity does not cause them to settle out over time. Potassium dichromate, K2Cr2O7, is an ionic compound composed of colorless potassium ions and orange dichromate ions. When a small amount of potassium dichromate is added to water, the compound dissolves and dissociates to yield potassium ions and dichromate ions uniformly, distributed throughout the mixture, as indicated in this equation here. As with the mixture of sugar and water, this mixture is also an aqueous solution. Its solutes, potassium and dichromate ions, remain individually dispersed among the solvent molecules. Water is used so often as a solvent that the word solution has come to imply an aqueous solution to many people. However, almost any gas, liquid, or solid can act as a solvent. Many alloys are solid solutions of one metal dissolved in another. For example, US 5-cent coins contain nickel dissolved in copper. Air is a gaseous solution, a homogeneous mixture of nitrogen, oxygen, and several other gases. Oxygen, alcohol, and sugar all dissolve in water to form liquid solutions. Table 11.1 gives examples of different solutions and the phases of the solutes and solvents. Solutions exhibit these defining traits. They are homogeneous after a solution is mixed. It has the same composition at all points throughout. Its composition is uniform. The physical state of a solution, solid, liquid, or gas, is typically the same as that of the solvents, as demonstrated by the examples, Table 11.1. The components of a solution are dispersed on a molecular scale. They consist of a mixture of separated solute particles, molecules, atoms, and/or ions, each closely surrounded by solvent species. The dissolved solute in a solution will not settle out or separate from the solvent. The composition of a solution, or the concentrations of its components, can be varied continuously, within limits determined by the solubility of the components discussed in later detail in this chapter. The formation of solutions. The formation of a solution is an example of a spontaneous process, a process that occurs under specified conditions without the requirement of energy from some external source. Sometimes a mixture is stirred to speed up the dissolution process, but this is not necessary. A homogeneous solution will form eventually. The topic of spontaneity is critically important to the study of chemical thermodynamics and is treated more thoroughly in a later chapter of this text. For purposes of this chapter's discussion, it will suffice to consider two criteria that favor but do not guarantee the spontaneous formation of a solution. One, a decrease in the internal energy of the system, an exothermic change, as discussed in the previous chapter on thermochemistry. Or two, an increased dispersal of matter in the system, which indicates an increase in the entropy of the system, as you will learn about later in the chapter on thermodynamics. One sec. There we go. Okay. In the process of dissolution, an internal energy change often, but not always, occurs as heat is absorbed or evolved. An increase in matter dispersal always results when a solution forms from the uniform distribution of solute molecules throughout the solvent. When the strengths of the intermolecular forces of attraction between the solute and solvent species in a solution are no different than those present in the separated components, the solution is formed with no accompanying energy change. Such a solution is called an ideal solution. A mixture of ideal gases, or gases such as helium and argon, which closely approach ideal behavior, is an example of an ideal solution, since the entities comprising these gases experience no significant intermolecular attractions. Okay. When the strengths of the intermolecular forces. Oh, no, I passed that already. Sorry. When containers of helium and argon are connected, the gases spontaneously mix due to diffusion and form a solution. The formation of this solution clearly involves an increase in matter dispersal, since the helium and argon atoms occupy a volume twice as large as that which each occupied before mixing. Ideal solutions may also form when structurally similar liquids are mixed. For example, mixtures of alcohols, methanol and ethanol form ideal solutions, as do mixtures of the hydrocarbons pentane and hexane. Placing methanol and ethanol, or pentane and hexane, in bulbs shown in Figure 11.3 will result in the same diffusion and subsequent mixing of these liquids as is observed for the helium and argon gases, although at a much slower rate, yielding solutions with no significant change in energy. Unlike a mixture of gases, however, the components of these liquid-liquid solutions do indeed experience intermolecular attractive forces, but since the molecules of the two substances being mixed are structurally very similar, the intermolecular attractive forces between like and unlike molecules are essentially the same, and the dissolution process therefore does not entail any appreciable increase or decrease in energy. These examples illustrate how increased matter dispersal alone can provide the driving force required to cause the spontaneous formation of a solution. In some cases, however, the relative magnitudes of intermolecular forces of attraction between solute and solvent species may prevent dissolution. Three types of intermolecular attractive forces are relevant to the dissolution process: solute-solute, and solvent-solvent, and solute-solvent. As illustrated in Figure 11.4, the formation of a solution may be viewed as a stepwise process in which energy is consumed to overcome solute-solute, and solvent-solvent attractions, and released when solute-solvent attractions are established. The relative magnitudes of the energy changes associated with these stepwise processes determines whether the dissolution process overall will release or absorb energy. In some cases, solutions do not form because the energy required to separate solute and solvent species is so much greater than the energy released by solvation. Consider the example of an ionic compound dissolving in water. Formation of the solute requires the electrostatic forces between the cations and anions of the compound to be overcome completely, as attractive forces are established between these ions and water molecules. Hydrogen bonding between a relatively small fraction of the water molecules must also be overcome to accommodate any dissolved solute. If the solute's electrostatic forces are significantly greater than the solvation forces, the dissolution process is significantly endothermic, and the compounds may not dissolve to an appreciable extent. Calcium carbonate, the major component of coral reefs, is one example of such an insoluble ionic compound. On the other hand, if the solvation forces are much stronger than the compound's electrostatic forces, the dissolution is significantly exothermic and the compound may be highly soluble. A common example of this type of ionic compound is sodium chloride, commonly known as table salt. As noted in the beginning of this module, spontaneous solution formation is favored but not guaranteed by exothermic dissolution processes. While many soluble compounds do indeed dissolve with the release of heat, some dissolve endothermically. Ammonium nitrate is one such example and is used to make instant cold packs, like the one pictured in Figure 11.5. Which are used for treating injuries. A thin-walled plastic bag of water is sealed inside a larger bag with solid ammonium nitrate. Then the smaller bag is broken. A solution of NH4NO3 forms, absorbing heat from the surroundings, the injured area to which the pack is applied, and providing a cold compress that decreases swelling. Endothermic dissolutions, such as this one, require a greater energy input to separate the solute species than is recovered when the solutes are solvated, but they are spontaneous nonetheless due to the increased disorder that accompanies formation of the solution. 11.2. Electrolytes. By the end of this section, you will be able to define and give examples of electrolytes, distinguish between the physical and chemical changes that accompany dissolution of ionic and covalent electrolytes, relate electrolyte strength to solute-solvent attractive forces. So when some substances are dissolved in water, they undergo either a physical or a chemical change that yields ions in solution. These substances constitute an important class of compounds called electrolytes. Substances that do not yield ions when dissolved are called non-electrolytes. If the physical or chemical process that generates the ions is essentially 100% efficient, then the substance is known as a strong electrolyte. If only a relatively small fraction of this dissolved substance undergoes the ion-producing process, it is called a weak electrolyte. Substances may be identified as strong, weak, or non-electrolytes by measuring the electrical conductance of an aqueous solution containing the substance. To conduct electricity, a substance must contain freely mobile charged species. Most familiar is the conduction of electricity through metallic wires, in which case the mobile charged entities are electrons. Solutions may also conduct electricity if they contain dissolved ions, with conductivity increasing as ion concentration increases. Applying a voltage to electrodes immersed in a solution permits assessment of the relative concentration of dissolved ions, either quantitatively by measuring the electrical current flow or qualitatively by observing the brightness of a light bulb included in the circuit. Ionic electrolytes. Water and other polar molecules are attracted to ions, as shown in Figure 11.7. The electrostatic attraction between an ion and a molecule with a dipole is called an ion-dipole attraction. These attractions play an important role in the dissolution of ionic compounds in water. When ionic compounds dissolve in water, the ions in the solid separate and disperse uniformly throughout the solution because water molecules surround and solvate the ions, reducing the strong electrostatic forces between them. This process represents a physical change known as dissociation. Under most conditions, ionic compounds will dissociate nearly completely when dissolved, and so they are classified as strong electrolytes. Even sparingly soluble ionic compounds are strong electrolytes, since the small amount that does dissolve will dissociate completely. Consider what happens at the microscopic level when solid KCl is added to water. Ion dipole forces attract the positive hydrogen end of the polar water molecules to the negative chloride ions at the surface of the solid, and they attract the negative ends of the positive potassium ions. The water molecules surround individual potassium and chloride ions, reducing the strong interionic forces that bind the ions together and letting them move off into solution as solvated ions, as Figure 11.7 shows. Ouch. Overcoming the electrostatic attraction permits the independent motion of each hydrated ion in a dilute solution as the ions transitioned from fixed positions in the undissolved compound to widely dispersed solvated ions in solutions. Covalent electrolytes. Pure water is an extremely poor conductor of electricity because it is only very slightly ionized. Only about 2 out of every billion molecules ionize at 25 degrees Celsius. Water ionizes when one molecule of water gives up a proton to another molecule of water, yielding hydronium hydroxide ions. In some cases, solutions prepared from covalent compounds conduct electricity because the solute molecules react chemically. For example, pure hydrogen chloride is a gas consisting of covalent HCl molecules. This gas contains no ions. However, an aqueous solution of HCl, very good conductor, indicating that an appreciable concentration of ions exists within the solution. Because HCl is an acid, its molecules react with water, transferring hydrogen ions to form hydronium ions and chloride ions. This reaction is likewise 100% complete for HCl. Likewise, weak acids and bases that only react partially generate relatively low concentrations of ions when dissolved in water and are classified as weak electrolytes. The reader may wish to review the discussion of strong and weak acids provided in the earlier chapter on this text on reaction classes and stoichiometry. 11.3 Solubility. Learning objectives. By the end of this section, you will be able to describe the effects of temperature and pressure on solubility, state Henry's law and use it in calculations involving the solubility of a gas and a liquid, explain the degrees of solubility possible for liquid-liquid solutions. Imagine adding a small amount of sugar to a glass of water, stirring until all the sugar has dissolved, and then adding a bit more. You can repeat this process until the sugar concentration of the solution reaches its natural limit, a limit determined primarily by the relative strengths of the solute-solvent, and solvent-solvent attractive forces discussed in the previous 2 modules of this chapter. You can be certain that you have reached this limit because no matter how long you stir the solution, undissolved sugar remains. The concentration of sugar in the solution at this point is known as its solubility. Hold on one sec. The solubility of a solute in a particular solvent is the maximum concentration that may be achieved under given conditions when the solution processes at equilibrium. When a solute's concentration is equal to its solubility, the solution is said to be saturated with that solute. If the solute's concentration is less than its solubility, the solution is said to be unsaturated. A solution that contains a relatively low concentration of solute is called dilute, and one with a relatively high concentration is called concentrated. Solutions may be prepared in which a solute concentration exceeds its solubility. Such solutions are said to be supersaturated, and they are interesting examples of non-equilibrium states. For example, the carbonated beverage in an open container that has not yet gone flat is supersaturated with carbon dioxide gas. Given time, the CO2 concentration will decrease until it reaches its solubility. Solutions of gases and liquids. As for any solution, the solubility of a gas in a liquid is affected by the intermolecular attractive forces between solute and solvent species. Unlike solid and liquid solutes, however, there is no solute-solute intermolecular attraction to overcome when a gaseous solute dissolves in a liquid solvent. Since the atoms or molecules comprising a gas are far separated and experience negligible interactions, consequently, solute-solvent interactions are the sole energetic factor affecting solubility. For example, the water solubility of oxygen is approximately 3 times greater than that of helium. There are greater dispersion forces between water and the larger oxygen molecules, but 100 times less than the solubility of chloromethane. Likewise, note the solubility of oxygen in hexane is approximately 20 times greater than it is in water because greater dispersion forces exist between oxygen and the larger hexane molecules. Temperature is another factor affecting solubility, with gas solubility typically decreasing as temperature increases. This inverse relation between temperature and dissolved gas concentration is responsible for one of the major impacts of thermal pollution in natural waters. When the temperature of a river, lake, or stream is raised, the solubility of oxygen in the water is decreased. Decreased levels of dissolved oxygen may have serious consequences for the health of the water's ecosystems and, in severe cases, can result in large-scale fish kills. The solubility of a gaseous solute is also affected by the partial pressure of solute of gas in the gas to which the solution is exposed. Gas solubility increases as the pressure of the gas increases. Carbonated beverages provide a nice illustration of this relationship. The carbonation process involves exposing the beverage to a relatively high pressure of carbon dioxide gas and then sealing the beverage container, thus saturating the beverage with CO2 at this pressure. When the beverage container is opened, a familiar hiss is heard as the carbon dioxide gas pressure is released, and some of the dissolved carbon dioxide is typically seen leaving solution in the form of small bubbles. At this point, the beverage is supersaturated with carbon dioxide, and with time, the dissolved carbon dioxide concentration will decrease to its equilibrium value, and the beverage will become flat. For many gaseous solutes, the relation between the solubility cap Cg and partial pressure cap Pg is a proportional one, where K is a proportionality constant that depends on the identities of the gaseous solute and solvent, and on the solution temperature. This is a mathematical statement of Henry's law. The quantity of an ideal gas that dissolves in a definite volume of liquid is directly proportional to the pressure of the gas. Like that. Great. Oops. Deviations from Henry's law are observed when a chemical reaction takes place between the gaseous solute and the solvent. Thus, for example, the solubility of ammonia in water increases more rapidly with increasing pressure than predicted by the law because ammonia, being a base, reacts to some extent with water to form ammonium ions and hydroxide ions. Gases can form supersaturated solutions. If a solution of a gas in a liquid is prepared either at low temperature or under pressure, or both, then as the solution warms or as the gas pressure is reduced, the solution may become supersaturated. In 1986, more than 1,700 people in Cameroon were killed when a cloud of gas, almost certainly carbon dioxide, bubbled from Lake Nyos, a deep lake and a volcanic crater. The water at the bottom of Lake Nyos is saturated with carbon dioxide by volcanic activity beneath the lake. It is believed that the lake underwent turnover due to gradual heating from below the lake, and the warmer, less dense water, saturated with carbon dioxide, reached the surface. Consequently, tremendous quantities of dissolved CO2 were released, and the colorless gas, which is denser than air, flowed down the valley below the lake and suffocated humans and animals living in the valley. Solutions of liquids in liquids. Some liquids may be mixed in any proportions to yield solutions. In other words, they have infinite mutual solubility and are said to be miscible. Ethanol, sulfuric acid, and ethylene glycol are examples of liquids that are completely miscible with water. Two-cycle motor oil is miscible with gasoline, mixtures of which are used as lubricating fuels for various types of outdoor power equipment. Miscible liquids are typically those with very similar polarities. Consider, for example, liquids that are polar or capable of hydrogen bonding. Drink. Consider, for example, liquids that are polar or capable of hydrogen bonding. For such liquids, the dipole-dipole attractions of the solute molecules with the solvent molecules are at least as strong as those between molecules in the pure solute or in the pure solvent. Hence, the two kinds of molecules mix easily. Likewise, nonpolar liquids are miscible with each other because there is no appreciable difference in the strengths of solute-solute, solvent-solvent, and solute-solvent intermolecular attractions. The solubility of polar molecules and polar solvents and of nonpolar molecules and nonpolar solvents is again an illustration of the chemical axiom like dissolves like. Two liquids that do not mix to an appreciable extent are called immiscible. Separate layers are formed when immiscible liquids are poured into the same container. Gasoline, oil, benzene, carbon, tetrachloride, some paints, and many other nonpolar liquids are immiscible with water. Relatively weak attractive forces between the polar water molecules and the nonpolar liquid molecules are not adequate to overcome much stronger hydrogen bonding between water molecules. The distinction between immiscibility and miscibility is really one of extent, so that miscible liquids are of infinite mutual solubility, while liquids said to be immiscible are of very low, though not zero, mutual solubility. Two liquids, such as bromine and water, that are of moderate mutual solubility are said to be partially miscible. Two partially miscible liquids usually form two layers when mixed. In the case of bromine and water mixture, the upper layer is water saturated with bromine, and the lower layer is bromine saturated with water. Since bromine is nonpolar and thus not very soluble in water, the water layer is only slightly discolored by the bright orange bromine dissolved in it. Since the solubility of water in bromine is very low, there is no noticeable effect on the dark color of the bromine layer. Solutions of solids and liquids. The dependence of solubility on temperature for a number of solids and water is shown by the solubility curves in Figure 1116. Reviewing these data indicate a general trend of increasing solubility with temperature, although there are exceptions, as illustrated by the ionic compound cerium sulfate. One sec. Okay. The temperature dependence of solubility can be exploited to prepare supersaturated solutions of certain compounds. A solution may be saturated with a lower compound at an elevated temperature, where the solute is more soluble, and subsequently cooled to a lower temperature without precipitating the solute. The resultant solution contains solute at a concentration greater than its equilibrium solubility at the lower temperature and is relatively stable. Precipitation of the excess solute can be initiated by adding a seed crystal, or by mechanically agitating the solution. Some hand warmers, such as the one pictured in 1117, take advantage of this behavior. 11.4. Colligative properties. By the end of this section, you'll be able to express concentrations of solution components using mole fraction and molality, describe the effect of solute concentration on various solution properties, perform calculations using the mathematical equations that describe these various colligative effects, describe the process of distillation and its practical applications, explain the process of osmosis, and describe how it is applied industrially and in nature. The properties of a solution are different from those of either the pure solute or solvent. Many solution properties are dependent upon the chemical identity of the solute. Compared to pure water, a solution of hydrogen chloride is more acidic, a solution of ammonia is more basic, a solution of sodium chloride is more dense, and a solution of sucrose is more viscous. There are a few solution properties, however, that depend only on the total concentration of solute species, regardless of their identities. These colligative properties include vapor pressure lowering, boiling point elevation, freezing point depression, and osmotic pressure. This small set of properties is of central importance to many natural phenomena and technological applications, as will be described in this module. Mole fraction and molality. Several units, commonly used to express the concentrations of solution components, were introduced in an earlier chapter of this text, each providing certain benefits for use in different applications. For example, molarity is a convenient unit for use in stoichiometric calculations since it is defined in terms of the molar amounts of a solute species. Because solution volumes vary with temperature, molar concentrations will likewise vary. When expressed as molarity, the concentration of a solution with identical numbers of solute and solvent species will be different at different temperatures due to the contraction expansion of the solution. More appropriate for calculations involving many colligative properties are mole-based concentrations, units whose values are not dependent on temperature, such units are mole fraction, introduced in the previous chapter on gases and molality. The mole fraction, X, is a component is the ratio of its molar amounts to the total number of moles of all solution components. So mole fraction of A equals the moles of A over total moles of all components. By this definition, the sum of mole fractions for all solution components is equal to 1. Molality is the concentration of unit defined as the ratio of the numbers of moles of solute to the mass of the solvent in kilograms. Since these units are computed using only masses and molar amounts, they do not vary with temperature and thus are better suited for applications requiring temperature-independent concentrations, including several colligative properties as well as described in this chapter module. Vapor pressure lowering. As described in the chapter on liquids and solids, the equilibrium vapor pressure of a liquid is the pressure exerted by its gaseous phase when vaporization and condensation are occurring at equal rates. Dissolving a non-volatile substance in a volatile liquid results in a lowering of the liquid's vapor pressure. This phenomenon can be rationalized by considering the effect of adding solute molecules on the liquid's vaporization and condensation processes. To vaporize, solvent molecules must be present at the surface of the solution. The presence of solute decreases the surface area available to solvent molecules and thereby reduces the rate of solvent vaporization. Thus, the rate of condensation is unaffected by the presence of solute. The net result is that the vaporization-condensation equilibrium is achieved with fewer solvent molecules in the vapor phase. While this interpretation is useful, it does not account for the several important aspects of the colligative nature of vapor pressure lowering. A more rigorous explanation involves the property of entropy, a topic of discussion in a later text chapter on thermodynamics. For purposes of understanding the lowering of a liquid vapor pressure, it is adequate to note that the more dispersed nature of matter in a solution compared to separate solvent and solute phases serves to effectively stabilize the solvent molecules and hinder their vaporization. A lower vapor pressure results in a correspondingly higher boiling point as described in the next section of this molecule. The relationship between the vapor pressures of solution components and the concentrations of those components is described by Raoult's law. The partial pressure exerted by any components of an ideal solution is equal to the vapor pressure of the pure component multiplied by its mole fraction in the solution, where Pa is the partial pressure exerted by component A in the solution, Pa star is the vapor pressure of pure A, and Xa is the mole fraction of A in the solution. Recalling that the total pressure of the gaseous mixture is equal to the sum of partial pressures for all its components, the total vapor pressure exerted by a solution containing I components is pressure of the solution equals the sum of all partial pressures. A non-volatile substance whose vapor pressure is negligible, and so the vapor pressure above a solution containing only non-volatile solutes is due only to the solvent. So the pressure of the solution equals mole fraction of the solution times pressure of the solvent. Distillation of solutions. Solutions whose components have significantly different vapor pressures may be separated by a selective vaporization process known as distillation. Consider the simple case of a mixture of two volatile liquids, A and B, with A being the more volatile liquid. Raoult's law can be used to show that the vapor pressure above the solution is enriched in component A, that is, the mole fraction of A in the vapor is greater than the mole fraction of A in the liquid. By appropriately heating the mixture, component A may be vaporized, condensed, and collected, effectively separating it from component B. Distillation is widely applied in both laboratory and industrial settings, being used to refine petroleum, to isolate fermentation products, and to purify water. A typical apparatus for laboratory scale distillations is shown in Figure 1119. Yeah. Oil refineries use large-scale fractional distillation to separate the components of crude oil. The crude oil is heated to high temperatures at the base of a tall fractionating column, vaporizing many of the components that rise within the column. As vaporized components reach adequately cool zones during their ascent, they condense and are collected. The collected liquids are simpler mixtures of hydrocarbons and other petroleum compounds that are of appropriate composition for various applications, as depicted in Figure 1120. Boiling point elevation. As described in the chapter on liquids and solids, the boiling point of a liquid is the temperature at which its vapor pressure is equal to ambient atmospheric pressure. Since the vapor pressure of a solution is lowered due to the presence of non-volatile solutes, it stands to reason that the solution's boiling point will subsequently be increased. Vapor pressure increases with temperature, so a solution will require a higher temperature than will pure solvents to achieve any given vapor pressure, including one equivalent to that of the surrounding atmosphere. The increase in boiling point observed when non-volatile solute is dissolved into solvent, delta Tb, is called boiling point elevation and is directly proportional to the molar concentration of solute species, delta Tb equals Kbm, where Kb is the boiling point elevation constant, or the ebullioscopic constant, and m is the molar concentration of all solute species. Boiling point elevation constants are characterized properties that depend on the identity of the solvent. Values of Kb for several solvents are listed in Table 11.2. The extent to which the vapor pressure of a solvent is lowered and the boiling point is elevated depends on the total number of solute particles present in a given amount of solvent, not on the mass or size or chemical identities of the particles. A 1 mole aqueous solution of sucrose and a 1 mole aqueous solution of ethylene glycol will exhibit the same boiling point because each solution has 1 mole of solute particles per kilogram of solvent. Freezing point depression. Solutions freeze at lower temperatures than pure liquids. This phenomenon is exploited in de-icing schemes that use salt, calcium chloride, or urea to melt ice on roads and sidewalks, and in the use of ethylene glycol as antifreeze in automobile radiators. Seawater freezes at a lower temperature than fresh water, and so the Arctic and Antarctic oceans remain unfrozen even at temperatures below 0 degrees Celsius, as do the body fluids of fish and other cold-blooded sea animals that live in these oceans. The decreasing and freezing point of a dilute solution compared to that of the pure solvent, delta Tf, is called the freezing point depression and is directly proportional to the molar concentration of the solute, where m is the molar concentration of the solute and Kf is the freezing point depression constant, or cryoscopic constant. Just as for boiling point elevation constants, these are characteristic properties whose values depend on the chemical identity of the solvent. Values of Kf for several solvents are listed in Table 11.2. Phase diagram for a solution. The colligative effects on vapor pressure, boiling point, and freezing point described on the previous section are conveniently summarized by comparing the phase diagrams for a pure liquid and a solution derived from that liquid. The liquid vapor curve for the solution is located beneath the corresponding curve for the solvent, depicting the vapor pressure, lowering delta P that results from the dissolution of non-volatile solute. Consequently, any given pressure, the solution's boiling point is observed at a higher temperature than that for the pure solvent, reflecting the boiling point elevation, delta Tb, associated with the presence of non-volatile solute. The solid-liquid curve for the solutions is displaced left of that for the pure solvent, representing the freezing point depression delta Tf that accompanies solution formation. Finally, notice that the solid gas curves for the solvent and its solution are identical. This is the case for many solutions comprising liquid solvents and non-volatile solutes. Just as for vaporization, when a solution of this sort is frozen, it is actually just the solvent molecules that undergo the liquid to solid transition, forming pure solid solvents that exclude solute species. The solid and gaseous phases, therefore, are composed of solvent only, and so transitions between these phases are not subject to colligative effects. Osmosis and osmotic pressure of solutions. A number of natural and synthetic materials exhibit selective permeation, meaning that only molecules or ions of a certain size, shape, or polarity, charge, and so forth are capable of passing through the material. Biological cell membranes provide elegant examples of selective permeation in nature, while dialysis tubing, used to remove metabolic wastes from blood, is a more simplistic technological example. Regardless of how they may be fabricated, these materials are generally referred to as semi-permeable membranes. Consider the apparatus illustrated in Figure 1124, in which samples of pure solvent and a solution are separated by a membrane that only solvent molecules may permeate. Solvent molecules will diffuse across a membrane in both directions, since the concentration of solvent is greater in the pure solvent than the solution. These molecules will diffuse from the solvent side of the membrane to the solution side at a faster rate than they will in the reverse direction. The result is a net transfer of solvent molecules from the pure solvent to the solution. Diffusion-driven transfer of solvent molecules through a semi-permeable membrane is a process known as osmosis. When osmosis is carried out in an apparatus like that shown in Figure 1124, the volume of the solution increases as it becomes diluted by accumulation of solvent. This causes the level of solution to rise, increasing its hydrostatic pressure and resulting in a faster transfer of solvent molecules back to the pure solvent side. When the pressure reaches a value that yields a reverse solvent transfer rate equal to the osmosis rate, bulk transfer of solvent ceases. This pressure is called the osmotic pressure of the solution. The osmotic pressure of a dilute solution is related to its solute molarity and absolute temperature, according to the equation, where R is the gas constant. If a solution is placed in an apparatus like the one shown in 1125, applying pressure greater than the osmotic pressure of the solution reverses the osmosis and pushes solvent molecules from the solution into the pure solvent. This technique of reverse osmosis is used for large-scale desalination of seawater on smaller scales to produce high-purity tap water for drinking. Oh. Okay. Examples of osmosis are evident in many biological systems because cells are surrounded by semi-permeable membranes. Carrots and celery that have become limp because they have lost water can be made crisp again by placing them in water. Water moves into the carrot or celery cells by osmosis. A cucumber placed in a concentrated salt solution loses water by osmosis and absorbs some salt to become a pickle. Osmosis can also affect animal cells. Solute concentrations are particularly important when solutions are injected into the body. Solutes in body cell fluids and blood serum give these solutions an osmotic pressure of approximately 7.7 atmospheres. Solutions injected into the body must have the same osmotic pressure as blood serum. That is, they should be isotonic with blood serum. If a less concentrated solution, a hypotonic solution, is injected in sufficient quantity to dilute the blood serum, Water from the diluted serum passes into the body or into the blood cells by osmosis, causing the cells to expand and rupture. This process is called hemolysis. When a more concentrated solution, a hypertonic solution, is injected, the cells lose water to the more concentrated solution, shrivel, and possibly die in a process called crenation. These effects are illustrated in Figure 1127. Determination of molar masses. Osmotic pressures and changes in freezing point, boiling point, and vapor pressure are directly proportional to the number of solute species present in a given amount of solution. Consequently, measuring one of these properties for a solution prepared using a known mass of solute permits the determination of the solute's molar mass. Colligative properties of electrolytes. As noted previously in this module, the colligative properties of a solution depend only on the number, not on the identity, of solute species dissolved. The concentration terms of the equations for various colligative properties pertain to all solute species present in the solution. For the solutions considered thus far in the chapter, the solutes have been non-electrolytes that dissolve physically without dissociation or any other accompanying process. Each molecule that dissolves yields one dissolved solute molecule. The dissolution of an electrolyte, however, is not this simple, as illustrated by the two common examples below. Considering the first of these examples and assuming complete dissociation, a 1 molal aqueous solution of sodium chloride contains 2.0 mole of ions per each kilogram of water, and its freezing point depression is expected to be delta Tf equals 2 moles ions per kilograms of water times 1.86 degrees Celsius kilograms of water per moles of ion equals 3.7 degrees Celsius. When this solution is actually prepared and its freezing point depression measured, however, a value of 3.4 degrees Celsius is obtained. Similar discrepancies are observed for other ionic compounds, and the differences between the measured and expected colligative property values typically become more significant as solute concentrations increase. These observations suggest that the ions of sodium chloride are not completely dissociated in solution. To account for this and avoid the errors accompanying the assumption of total dissociation, an experimentally measured parameter named in honor of Nobel Prize-winning German chemist Jacobus Henricus van 't Hoff is used. The van 't Hoff factor is defined as the ratio of solute particles in solution to the number of formula units dissolved. Values for the measured van 't Hoff factors for several solutes, along with predicted values assuming complete dissociation, are shown in Table 11.3. In 1923, the chemists Peter Debye and Henrik Huckel proposed a theory to explain the apparent incomplete ionization of strong electrolytes. They suggested that although interionic attraction in an aqueous solution is greatly reduced by solvation of the ions and the insulating action of the polar solvent, it is not completely nullified. The residual attractions prevent the ions from behaving as totally independent particles. In some cases, a positive and negative ion may actually touch, giving a solvated unit called an ion pair. Thus, the activity or the effective concentration of any particular kind of ion is less than that indicated by the actual concentration. Ions become more and more widely separated and more dilute the more that dilute the solution, and the residual interionic attractions become less and less. Thus, in extremely dilute solutions, the effective concentrations of the ions are essentially equal to the actual concentrations. Note that the van 't Hoff factors for the electrolytes in Table 11.3 are for 0.05 molal solutions, at which concentrations the value of I for NaCl is 1.9, as opposed to an ideal value of 2. 11.5, learning of colloids. By the end of this section, you'll be able to describe the composition and property of colloidal dispersions, list and explain several technological applications of colloids. As a child, you may have made suspensions such as mixtures of mud and water, flour and water, or a suspension of solid pigments and water, known as tempera paint. These suspensions are heterogeneous mixtures of relatively large particles that are visible, or that can be seen with a magnifying glass. They are cloudy, and the suspended particles settle out after mixing. On the other hand, a solution is a homogeneous mixture in which no settling occurs, and in which the solutions or the dissolved species are molecules or ions. Solutions exhibit completely different behavior from suspensions. A solution may be colored, but it is transparent. The molecules or ions are invisible, and they do not settle out or on standing. Another class of mixtures called colloids or colloidal dispersions exhibit properties intermediate between those of suspensions and solutions. The particles of a colloid are larger than most simple molecules. However, colloidal particles are small enough that they do not settle out upon standing. The particles in a colloid are large enough to scatter light, a phenomenon called the Tyndall effect. They can make colloidal mixtures. This can make colloidal mixtures appear cloudy or opaque, such as the searchlight beams shown in Figure 1130. Clouds are colloidal mixtures. They are composed of water droplets that are much larger than molecules, but that are small enough that they do not settle out. The term colloid, from the Greek word kala, means glue, and eidos, meaning like, was first used in 1861 by Thomas Graham to classify mixtures such as starch and water and gelatin. Many colloidal particles are aggregates of hundreds or thousands of molecules, but others, such as proteins and polymer molecules, consist of an extremely uh, large molecule. The protein and synthetic polymer, single extremely large molecule. The protein and synthetic polymer molecules that form colloids may have molecular masses ranging from a few thousand to many million atomic mass units. Analogous to the identification of solution components as solute and solvent, the components of a colloid are likewise classified according to their relative amounts. The particulate component, typically present in a relatively minor amount, is called the dispersed phase, and the substance or solution throughout which the particulate is dispersed is called the dispersion medium. Colloids may involve virtually any combination of physical states, gas and liquid, liquid and solid, solid and gas, etc., as illustrated by the examples of colloidal systems given in Table 11.4. Preparation of colloidal systems. Colloids are prepared by producing particles of colloidal dimensions and distributing these particles throughout a dispersion medium. Particles of colloidal size are formed by two methods. Dispersion methods, breaking down larger particles. For example, paint pigments are produced by dispersing large particles by grinding in special mills. And two, the condensation methods. Growth from smaller units such as molecules or ions. For example, clouds form when water molecules condense and form very small droplets. A few solid substances, when brought into contact with water, disperse spontaneously and form colloidal systems. Gelatin, glue, starch, and dehydrated milk powder behave in this manner. The particles are already of colloidal size. The water simply disperses them. Powdered milk particles of colloidal size are produced by dehydrating milk spray. Some atomizers produce colloidal dispersions of a liquid in air. An emulsion may be prepared by shaking together or blending two immiscible liquids. This breaks one liquid into droplets of colloidal size, which then disperse throughout the other liquid. Oil spills in the ocean may be difficult to clean up, partly because wave action can cause the oil and water to form an emulsion. In many emulsions, however, the dispersion phase tends to coalesce, form large drops, and separate. Therefore, emulsions are usually stabilized by an emulsifying agent, a substance that inhibits the coalescence of the dispersed liquid. For example, a little soap will stabilize an emulsion of kerosene in water. Milk is an emulsion of butterfat in water, with the protein casein serving as an emulsifying agent. Mayonnaise is an emulsion of oil and vinegar, with egg yolk components of the emulsifying agents. Condensation methods form colloidal particles by aggregation of molecules or ions. If the particles grow beyond the colloidal size range, drops or precipitates form, and no colloidal systems result. Clouds form when water molecules aggregate and form colloid-sized particles. If these water particles coalesce to form adequately large water drops of liquid water or crystals of solid water, they settle from sky as rain, sleet, or snow. Many condensation methods involve chemical reactions. A red colloidal suspension of iron 3 hydroxide may be prepared by mixing a concentrated solution of iron 3 chloride with hot water. A colloidal gold solution results from the reduction of a very dilute solution of gold 3 chloride by a reducing agent such as formaldehyde, tin 2 chloride, or iron 2 sulfate. Some gold sols prepared in 1857 are still intact. The particles have not coalesced and settled, illustrating the long-term stability of many colloids. Soaps and detergents. Pioneers made soap by boiling fats with a strongly basic solution made by leaching potassium carbonate, which is K2CO3, from wood ashes with hot water. Animal fats contain polyesters of fatty acids, long-chain carboxylic acids. When animal fats are treated with a base like potassium carbonate or sodium hydroxide, glycerol and salts of fatty acids such as palmitic, oleic, and stearic acids are formed. The salts of fatty acids are called soaps. The sodium salt of stearic acid, sodium stearate, has the formula C17H35CO2Na and contains an uncharged nonpolar hydrocarbon chain, the C17H35 unit, and an ionic carboxylate group, the CO2- unit. Detergents, soap substitutes, also contain nonpolar hydrocarbon chains such as C12H25 and an ionic group such as sulfate, OSO3, or sulfonate, SO3-. Soaps form insoluble calcium and magnesium compounds in hard water. Detergents form water-soluble products, a definite advantage for detergents. The cleaning action of soaps and detergents can be explained in terms of the structures of the molecules involved. The hydrocarbon end of the soap or detergent molecule dissolves in or is attracted to nonpolar substances such as oil, grease, or dirt particles. The ionic end is attracted by water, illustrated in Figure 1133. As a result, the soap or detergent molecules become oriented at the interface between the dirt particles and the water, so they act as a kind of bridge between two different kinds of matter, nonpolar and polar. Molecules such as this are termed amphiphilic, since they have both hydrophobic part and a hydrophilic part. As a consequence, dirt particles become suspended as colloidal particles and are readily washed away. Electrical properties of colloidal particles. Dispersed colloidal particles are often electrically charged. A colloidal particle of iron-3 hydroxide, for example, does not contain enough hydroxide ions to compensate exactly for the positive charges on the iron-3 ions. Thus, each individual colloidal particle bears a positive charge, and the colloidal dispersion consists of charged colloidal particles and some free hydroxide ions, which keep the dispersion electrically neutral. Most metal hydroxide colloids have positive charges, whereas most metals and metal sulfides form negatively charged dispersions. All colloidal particles in any one system have charges of the same sign. This helps keep them dispersed because particles containing like charges repel each other. The charged nature of some colloidal particles may be exploited to remove them from a variety of mixtures. For example, the particles comprising smoke are often colloidally dispersed and electrically charged. Frederick Cottrell, an American chemist, developed a process to remove these particles. The charged particles are attracted to highly charged electrodes, where they are neutralized and deposited as dust. This is one of the important methods used to clean up the smoke from a variety of industrial processes. The process is also important in the recovery of valuable products from the smoke and the flue dust of smelter furnaces and kilns. There are also similar electrostatic air filters designed for home use to improve indoor air quality. And gels. Gelatin desserts such as Jell-O are a type of colloid. Gelatin sets on cooling because the hot aqueous mixture of gelatin coagulates as it cools, yielding an extremely viscous body known as a gel. A gel is a colloidal dispersion of a liquid phase throughout a solid phase. It appears that the fibers of the dispersing medium form a complex three-dimensional network, the interstices being filled with the liquid medium or a dilute solution of the dispersing medium. Pectin, a carbohydrate from fruit juices, is a gel-forming substance important in jelly making. Silica gel, a colloidal dispersion of hydrated silicon dioxide, is formed when dilute hydrochloric acid is added to a dilute solution of sodium silicate. Canned heat is a flammable gel made by mixing alcohol and a saturated aqueous solution of calcium acetate. And that is it for Chapter 11.